So for the tutorial question, an adiabatic gas turbine expands air at 1300 kilopascal and 500 degrees Celsius to 100 kilopascal and 127 degrees Celsius. 1300 kilopascal and 500 degrees Celsius will be P1 and T1. 100 kilopascal and 127 degrees Celsius will be P2 and T2. Air enters the turbine through a 0.2 meter square opening with an average velocity of 40 meter per second and exhausts through a 1 meter square opening. So 0.2 meter square will be A1, 40 meter per second will be V1, 1 meter square will be A2. So this is our schematic diagram of turbine. So the air will enter the inlet and this is the system in the turbine and will go out through the outlet. So we need to determine the mass flow rate of air through the turbine and power produced by the turbine.
For this question, we know that rate of net energy transfer by heat, work, and mass is equal to rate of change in internal kinetic and potential energies. So the assumptions made are, it is a steady process, an adiabatic system, the air behaves as an ideal gas, and the change in potential energy is negligible since the height change is too small. So as we know that it is a steady process, delta E system over delta T will be cancelled off, and we will get E in minus E out is equal to 0. So this is the equation that we will get. Since we know that it is an adiabatic system, Q in and Q out will be cancelled off, as well as W in as there is no work supply from external source. And lastly, the change in potential energy is negligible, and we will just assume it to be 0.
As mentioned earlier, since Q in, W in, potential energy and Q out cancel out, we will come to the final overall energy balance of turbine, which is W out equals to the total rate of energy transport by mass at the inlet minus the total rate of energy transport by mass at the outlet without involving potential energy. W out is involved as turbine will produce power output unlike compressor. Enthalpy is involved because the system is an open process where workflow is needed to maintain a continuous flow through a controlled volume. Kinetic energy is involved too because there is change in velocity of fluid due to the change in cross-sectional area of the pipe inlet and outlet.
For question 6a, since we assume that air is an ideal gas, we can use the ideal gas equation to find the specific volume of air at inlet and outlet. The gas constant of air can be gained from the table A1. Since this is an open and steady process as mentioned before, the mass flow rate entering and leaving the turbine are equal. We derive the equation N to find the mass flow rate cross-section area times the velocity and divide by the specific volume. Actually, we can simply use all inlet data to solve the problem, but we choose to find value of velocity outlet and use it to determine the mass flow rate of air through the turbine, which is 46.87 kg per second.
Power or rate of work done by turbine is obtained using the energy balance equation derived earlier. After rearranging, power equals to the sum of net change in enthalpy and kinetic energy. Delta H also equals to the product of mass flow rate, average specific heat capacity at constant pressure, and temperature difference between inlet and outlet stream. Cp average is obtained through table A2 by interpolating the value of Cp with average temperature. Finally, after substituting all the values including the value of outlet velocity obtained in 6a, the power produced by the turbine is 18.3 MW.